So today we have Carlos. I have forgot when I met you for the first time, Carlos. When was that?
I think it was in Barcelona, in one of my visits there to
Maybe.
to Carlos
Or in Granada.
or maybe I think maybe we organized this journey on gravitational waves on Granada.
Yes, at the Institute
Yeah,
of Astronomy and
a long time
Astrophysics,
ago.
yes. I remember talking to,
Exactly.
yes, it was Jose Luis, yes.
Exactly. It was our
Yes, yes. And I pretended that I knew some things about gravitational waves, and you believed me. Yes. Okay, so Carlos is a very nice person, like the rest of them, and I really, really encourage you that you interrupt him as many times as you want, because he will have an interesting answer for you. So, Carlos, go ahead.
Okay. What I'm going to tell you about in this talk is I'm going to present a line of research that I'm not sure whether you are going to be very familiar or not. The title of the talk, it will be something like viability of an emergent gravity theory from condensed matter-like systems. So let me explain why this title comes about. The thing is that there are important reasons to expect that we have to transcend general relativity. And these reasons, from the one side, we have classical reasons, in the sense that classical general relativity leads to, for example, to singularities, both inside black holes and also in the origin of the universe or cosmological situations. And then there is other problems with gravity when you try to combine gravity with quantum mechanics in different ways. So in both cases, people, I think that most people most people would be share the idea that we have to transcend general relativity in some regimes, not everything. There will be regimes in which general relativity would be a very, very good approximation, but then there will be other regimes in which we have to substitute or modify this theory by something else. And then, in order to do that, there are different approaches. There are, from the more theoretical, more quantum side, we have this string theory, in which you can find formally a theory of quantum gravity. And then there is the other more popular approach is loop quantum gravity, in which you you extend the canonical formalism to quantizing the gravitational field, and you go to these new variables and these new techniques to be able to succeed on that. But there are other approaches like, I don't know, causal sets or causal dynamical triangulations. But here I'm going to talk about another approach, which is more minority, but it's very different from the ones that I have mentioned before. And it's the following. In a sense, what I'm going to talk about is that we want to check the following thesis. And is, can gravity, as we know it, I mean, general relativity, be something, an epiphenomenon, meaning that it can be derived from a condensed matter-like system? So that's the question that we would like to answer. And what do we mean by that? So the thing is that we would like to see whether the gravitational characteristics, all of the gravitational characteristics, can can appear. What do we call this emergent gravity? We call this emergent because we are trying to obtain these gravitational characteristics starting from systems in which you don't see any of the characteristics of neither special relativity nor of general relativity. The thing is that in other approaches, for example, if you compare with loop quantum gravity, loop quantum gravity start from the structure of classical GR, and then you try to, it is guided by the structure of general GR in order to get a quantum theory, with the hope that once you have the quantum theory, you will be able to find a regime in which you recover the classical theory. But here we go one step further, in the sense that the theory itself that we start from is something that doesn't have, in principle, any characteristics that you would consider relativistic, in a sense. And that's why we used to call it emergent gravity, because it's something that if you give one of these systems to someone that doesn't know anything about them, it would be very difficult to guess that inside these systems you can find low effective physics mimicking or resembling relativistic ideas. So, which are the main ingredients of a theory like that? The main ingredients is we are going to start from n-body quantum mechanical system living in a Galilean world. That's why we mean that we are condensed, and we say that is matter-like, because we are not saying that we are not using the precise condensed matter systems that we know that exist. Instead, we just have this abstract many-body quantum mechanical system, and then we try to see whether there exists some interactions between these atoms, or, well, particles, if you want, so that there exists some regime in which you can find these relativistic regimes.
Hi, Carlos.
Yes.
I have a question, but first I think Diana wants to ask a question as well, so I will ask her to ask if she wants, and then I would have mine.
Fine.
Diana? Or Benny, do you want to ask? Well, I'll go ahead with my question. You said the ingredients would be n-body system. It's a quantum system in Galilean space. So that would be Galilean, meaning time-space is the same no matter how far away, or?
Yeah, by Galilean, I mean the same space that Newton was using. I mean an absolute Euclidean space and time.
So in this case, the expectation, I suppose, is that a sufficiently large number of bodies that are a quantum system, they will, at large scales, interact with other groups they would generate gravity. They would generate something like a gravitational interaction.
Yes, I will explain that. Yeah.
Okay. Thanks.
Any other question at this point?
I think, Diana wants to ask, but somehow she's having problems, so I guess she will try in another moment.
Okay. Whenever you're ready, you just interrupt. So the thing is that the two ingredients that I was saying is that Is it working properly, my microphone?
Yes, I can hear you.
Okay.
Yes, very well.
Okay. The thing is that, so as I said, the main ingredient is this n-body quantum mechanical system in this absolute space, and time, a Newtonian space-time. Why a Galilean world? Why this hypothesis? This hypothesis comes about not because I believe or something that the world is eventually at the end of in deeper layers of reality is really Galilean. It's because it's a hypothesis, a working hypothesis that allows to see that it's very simple in the sense that it's a kind of the simplest geometrical structure you can impose in a system with the dimensionality, and it serves to make proofs of principle of whether, starting from these things, you can get things that are from the low energy perspective are more relativistic in a sense, and you will see. And then why a quantum system? Why this quantum mechanical system? Again, it's because we know that what we want to reproduce is something that has at least the material degrees of freedom. We know that there are quantum. So the simplest way to get some low energy description which has this quantum mechanical behavior is that you start from some quantum mechanics as a baseline, and then you will recover some quantum properties in some sectors of your eventual theory. But this does not commit with the idea that the world should be at a deeper layer to be quantum. It might be that quantum mechanics is also an emergent property, but again, it's trying to get some basic language in order to be able to work forward. And why are we interested in this approach? Well, there are many reasons for that. One thing is, for example, that it can provide explanations where other approaches just work by hypothesis. It's like, for example, in relativity, you assume that you have a causality of one particular form, special relativity, and then you work out the the conclusions that can be derived from that. But in this approach, because you are not starting from a relativistic invariance anywhere, then if you find a regime in which these relativistic invariants appear, then you have sort of an explanation of how these things could appear in places in which initially they were not. And also the hope is that by analyzing how these theories work, the biggest hope is that we will be directed to new effects that we can test and new effective descriptions. There are, in a sense, the first deviations, the expected first deviations from the standard general relativistic behaviors.
Excuse me?
Yes.
Can you hear me?
Yes.
Okay. I would like to know if you could explain a little bit more, please. What is loop quantum gravity? You told it before, but my microphone wasn't working properly. Sorry.
Okay, but can you repeat the question?
You mentioned before loop quantum gravity.
Yes.
At the beginning. Could you explain it a little more, please?
Okay. What is loop quantum gravity? Well,
yeah.
loop quantum gravity is sort of an evolution of the idea of quantizing gravity in a canonical way, meaning that you have a specific foliation of space-time and you have some variables the metric and the momenta of the metric, the derivatives, if you want, the variation of the metric with a time variable. And then these are the variables, this metric on a hypersurface plus the momenta of the metric. They build up a canonical system as the standard canonical systems in which you have Q's and P's to deal with. And then once you have this canonical formulation, you can try to quantize the system as you are doing with other quantum mechanical systems. And then this program is it has been developed from a long time ago, and in the version in which you use these variables, you find a lot of problems. But then people start realizing that there are other ways of progressing within the same paradigm by changing the variables that you use to quantize the system. And then you change, for example, from the G's and the momentum, you change variables to the connections, what is called the Assecar-Barbero connection, and the tetrads, the tetrad fields. Well, the triads, it's better, the triads, which are sort of the square roots of the metric inner slice of space-time. And then by using different techniques, then you can have a lot of progress on the idea of quantizing gravity. But it's a program which is still in progress, because there are some things that have been very successful, but there are still some things like solving the evolution, the what is called the Hamiltonian constraint, which is not that simple, and that people are still working on that.
Thank you.
Okay. So one nice thing of this of the approach that I am telling you about, it is that if we manage to get something which is similar to GR, to general relativity within this approach, then by the same price, we will show that there are many, that you have built not a single quantum gravity theory, but a universal family of them. We also approve a principle that that there are many ways of dealing with microscopic degrees of freedom that they could lead to the same effective physics in some regimes, and that only when you really are able to prove the microscopic physics, then you will realize whether you are in one theory or another. But by just checking the first deviations from general relativity, probably it would be not enough to know which is the actual theory working in
work on your subject.
This is unbelievable. I mean, it has been a cutting in the electricity. It never happened to me in 2 years. My God. So it took a while for all the systems to reboot. Okay. Sorry about that. I'm very sorry about that.
No, it's
Don't
fine.
worry.
Okay, so how we continue? I was mentioning this idea. Well, so the thing is that let's go to some partial results already in this line of research. And with these partial results, you will see what do we have in mind. So we, in order to try to lead to completion this program, which is quite complicated from the constructive point of view, we started to analyze simpler examples of how emergent physics could work out. And the first thing that we try to do is to construct an emergent theory of electrodynamics. And for that, what we did is to follow the ideas previously of a Russian professor, Professor Bolovic, which has been playing with these ideas for a long time. And then what we try to see is whether, starting from systems which are very similar to helium-3, we are going to be able to build something similar. Well, it's a faithful similarity. So we wanted to construct this emergent electrodynamic theory. So the thing is that it is possible to do it. The result is that it is possible to do it. And let me explain about along which lines this happen. The thing is that when you have, imagine that you have a system of spin 1/2 particles, atoms, neutral things, doesn't have a charge. These are similar to the helium-3 atoms. These are spin 1/2 systems. And then you put them into interaction. And the thing is that if the interactions between these systems, between these atoms, are such that they have a repulsive core, but then an attractive bound state, potentials we have sort of a Mexican hat form. Well, not a Mexican hat. I mean, they have a central bump, meaning that you have this repulsive core, but then you have a negative region around the central core, which allowed for bound states. And this is typical from the helium liquids. And then if in this situation, what happens is that when you lower very much the temperature of helium-3, it enters into a superfluid state. And the superfluidity in helium is controlled by the fact it's very similar to the BCS, to the Bardeen-Schiffer-Cooper superconductivity in metals, in the sense that what happened is that there is, at very low temperatures, what happened is that there is the formation of Cooper pairs in the system. Is that two atoms form combined systems, and the difference between superfluidity in helium and the standard superconductivity in metals is that the condensation in helium doesn't occur in the S sector, in the S wave sector, but it happened in the P wave sector. This means that the Cooper pairs that appears in helium, they have an angular momentum instead of being things without angular momentum. And also because you have, in fact, when you lower enough the temperature in one of these helium systems, what you have is that you enter into a phase, the superfluid phase, in which you have an order parameter which is quite complex. It's a matrix, a 3x3 matrix, which have an orbital index and an spin index. It's like if you have L equal 1, S equal 1 combinations. And the system, depending on the temperature and also depending on the specific interactions between these atoms, it can end up into different vacuum configurations. And the ones that are well known in the helium, in the real helium, is the so-called A phase and the B phase. They are the two more standard phases. But there is another phase which is also supposed to be to exist in some narrow bands in the real systems, which is called the planar phase. And this is the one that we are going to assume, is that imagine that you have, because now, as I said before, what you have is that you control the interactions between these things, you prescribe them in order that the system acquire this special vacuum state, which is this planar phase. And what is the planar phase? The planar phase means that, as I said, these Cooper pairs, which is pairs of two helium atoms, are such that they have you can have pairs with the two spins up. But then what happens is that in the planar phase is that if you pair two things with the spins up, the angular momentum is also, well, it can have any direction, but you have a particular direction for the angular momentum. But if the spins are down, then the angular momentum of the pair is just on the opposite direction that for the spins up. And this makes this state very special in the sense that it has an axis, a special axis, but it doesn't have axiality because as the angular momentum of the pairs, some of them are in one direction and some of the other are in the other direction, they don't have, in a sense, they don't have an arrow. They don't show an arrow. They just show a line. Everything is okay with the sound?
Yes, very well.
Okay.
A question on that. So this would mean basically that each pair has a null momentum, but still the line along which they are aligned is preferential.
No, right? So momentum. No, they have all the pairs. They have L equal 1 angular momentum. So they are rotating. In a sense, these pairs are rotating these are like a small planetary system. Rotating around each other in this sense of having this angular momentum. But the thing is that momentum are aligned. They just point in one. They can run one direction or in the other. So this, in a sense, well, what you say is that the system totally doesn't have an angular momentum. That's right. The total system is not rotating because you have as many pairs rotating in one direction that pairs rotating on the other direction. And in this sense, that's why this vacuum state is not axial. It doesn't have an axial symmetry.
And what would prevent the system from, so the two atoms that are aligned, what would prevent them to form a molecule?
Well, precisely what I was saying before is that they form a sort of molecule, but the thing is that they don't collapse in each other because there is this repulsive core in the potential between the interaction between any two atoms. I mean, they try to attract, when they are very far apart, they try to attract to each other, but when they are very close by, they try to repel. And then they find like a specific distance that they are happy with. And that's why, and that's the difference with the superconductivity. In superconductivity, the combination of two electrons, an electron hole, if you want, in the superconductivity. Well, two electrons that are traveling in the thing is that these things do not have an angular momentum. They travel as if they were, I mean, they prefer to be very close by to each other because the attraction now is in the S wave. It's just like a normal potential. It's like a normal potential. Here, instead, the potential is going down, but then it goes up in the center and then goes down again. So everything depends on the specific characteristics of the interactions between the atoms, okay? And also these interactions control in which vacuum states you can end up in specific regimes. Well, the next thing.
But just to see if I understood correctly, so the situation that makes this system of hydrogen atoms not form molecules is the very low temperatures. Is that a good way of thinking of it, or?
Well, I'm not sure what you mean by molecules. I mean, the thing is that you have, it is true that, I mean, it's a liquid. It's a liquid, meaning that you have a lot of atoms. The helium liquid is such that because the atoms are fermions, well, it's not only because of that. I mean, the thing is that the helium allows for the system to be in a compact way that cannot be more compact. I mean, it has a pressure that meaning that if you try to compress helium, it will not allow you to do it as much. I mean, it will have a resistance to do that. So the thing is that the atoms, they repel to each other when you try to put them too close together. And in a sense, you can backtrack this to the very repulsive nature of the spins. But then when you have, the vacuum state can acquire these different characteristics in the sense that the vacuum forms these Cooper pairs, and then it can condense. There are most of the atoms in the systems are in the vacuum, are in this condensed phase. And then and this is what provides the superfluid characteristics of helium. And this happens only at very low temperatures, because at very low temperatures, the very tiny interactions that are able to build up these pairs are not destroyed by the thermal fluctuations. If you are at higher temperatures, then you don't have, well, it's similar to what happened with superconductivity. If you are at much higher temperatures, these bindings between these two electrons in a crystal, they are not able to bind to each other. Okay.
I see. Thanks.
Okay. So the thing is that
not too long. Could you quickly say what the A and B states are in comparison to the state you just described?
Yeah, these two states are different from the planar states that I was mentioning. Well, the E phase is something in which for the two spins up, you have a line for the angular momentum, but for the spins down, you have the same angular momentum. The thing is that the A phase, it really has all the pairs, they have the same angular momentum direction. So you have you have an axis, but you have more than an axis. You have an arrow in the system, a precise arrow in the system. And the B phase is different, because in the B phase you have an angle between the spins, the spin 1 and the L1 characteristics, that the angle between the spins and the angular momentum is always the same. But then you have pairs with all the directions of the combination. And then this means that the overall, there is no any axial characteristic. For example, there is no any axis, because you can find angular momentum in all the directions of the system. So this system is very different. It's not axial. It's more isotropic, if you want, the B phase. And these are the superfluid phases of helium. But the nice thing of the planar phase is that when you, and that's the logic that I want to, that's the most important part of the logic that I want you to take home, is that once you analyze the vacuum state, and then you first go to the lowest temperatures, you find that there is a specific vacuum state for the system. And then you try to analyze which is the form of the lowest excitations that you can build on the system. Because at very low temperatures, these low energy excitations are the ones that are going to control the physics, your physics. And then what happened is that when you analyze what the form of the low energy excitations in this helium-like in the planar phase, what happened is that you find that the excitations are they follow an equation, which is the Dirac equation. It's a massless equation with a sonic velocity, which is finite and is equal for all the wavelengths. So you find a regime in which all the excitations are relativistic, and they have the form of a Dirac equation. And it's even more. I mean, and let me explain a few things about that. First of all, the presence of the sound velocity is not difficult to imagine. Is that you have a system that even though any of the particles can travel at whatever velocity, because they are living in a Galilean world, the thing is that when you have them at rest initially and then you are just analyzing perturbations on that, you have collective excitations, and the collective excitations, they do exhibit a sonic velocity. And this, but here there is even a more funny thing, and is that this system has what is called Fermi points, meaning that there are excitations that do not have a gap on energy to excite them. They don't have mass. And all the excitations that are living close to the Fermi points, which in this case, the Fermi points are located on the axis of symmetry of the planar phase. So you have excitations which are living. There are two Fermi points which are living in the same axis, but one in the north, in a north pole, and one in a south pole. The thing is that excitations that are living close to these Fermi points behave as Weyl spinors, precisely the formula of Weyl spinor. But then, because you have two types of Weyl spinors, one in the upper Fermi point and another one in the south Fermi point, what happens is that you can combine them and you form a four-component Weyl spinor. A four-component Dirac spinor. So at the end of the day, the thing is that, summarizing, is that you have these atoms. Your initial system is built up of just spin 1 atoms. But then the collective spin wave excitations of these things, when you are in the vacuum state, you have this drop of helium. You put this into the lowest temperature situation, and then you try to excite the drop in a way. So what the first thing that you find is that there are some spin waves on the system, and these spin waves can be described with precisely Dirac equation, with two spins up and a spin down, plus something which is a charge. There is the emergence of a new property, which is precisely the charge of the system, whether it is an electron or it is an effective electron or it is an effective positron. And the charge, this effective charge, is coming from the fact that the system has two Fermi points, and then you have excitations living close to both of them. And if the excitation lives in one of the poles, then in one of the Fermi points, then it has a positive charge. And if it lives in the other, then it's negative charge. So that's the first funny thing that happened. So you have built a Minkowski-Dirac equation living in our formal language, living in a Minkowski spacetime. But then you can go further because then.
Sorry.
Yes.
If I may, so how is it possible the system can have a charge while all atoms are neutral?
Exactly. That's the first very, well, I think, interesting result, is that, as you say, the system, it doesn't have charge. These are neutral atoms and they have just spin. But then there is a new property that appears in the excitations from the vacuum, that is this living in the Fermi surface, the typical Fermi surface. Now it has two special points, which are the points that are living in the axis of symmetry. Meaning that if you have a spin wave on the system, which travels precisely along the axis, it has special properties. And it can travel along the axis in the positive direction or in the negative direction. So these two propagations are such that at the end they add a new characteristic to the spin wave, and you can prove that this new characteristics is equivalent to a charge.
Okay, but that's how they behave. Can you hear me?
Yes.
That would be how they behave in the equations. They would behave as charged particles behave in such equations, right?
Exactly.
So how do we? And this is, of course, is not that the whole system has a charge itself. Is that one of the excitations behaves like a quantum particle that is described by a wave, and it would be like a quantum particle that has a charge.
Yes.
So it's a relativistically moving excitation. Okay. So it's a quasi-particle. Can we say that?
It's a collective excitation, which is a quantum collective excitation, which is a quasi-particle. And this quasi-particle is such that it has an equation, which is the Dirac equation. So you have 4 types. If you don't want to call this yet charge, that's fine. Up to now, what we have is that we have 4 different things, 4 types of spin waves on the system, with the spins ups and down, and another characteristic, but I call it charge.
Right, and the axis, right, and the axis that you mentioned is the axis of alignment of all the spins, I imagine.
The axis is the alignment of all the angular momentum of the Cooper pairs.
Right. So at these low temperatures, we would expect that the system will align itself completely. And okay.
Yes.
Very interesting.
This charge is not surely not an electric charge of units of electric charge, but it's something that determines the interaction of those excitations, right?
Yes. At this stage, it's just a label, an additional label that separates different things.
And then if it determines the interactions, so if it has a certain value, what sets the scale of this value?
Well, the length, the scale of this is the so-called the momentum of the Fermi point, which is a specific value of the momentum at which the Fermi point is located. So in a sense, is the from the perspective of the lab, which is the typical momentum that a Cooper pair will have, the magnitude of the momentum of one of these Cooper pairs.
Thank you.
Which are traveling in one particular direction. So the next stage is when you have that, is that in the systems you have, and this is, I think, one of the most important lessons, is that the system has 2 types of collective excitations. There is collective excitations which are quantum-like, which are not, they have fermionic characteristics. These are Fermi spin waves, and they have quantum characteristics, even though they are quasi-particles. But then there is also perturbations of the vacuum state itself. And the thing is that once you create some excitations on the Dirac sector, if you want, you also have to produce some modification of the vacuum state itself, some deformation of the vacuum. And then what is possible to prove is that the deformations of the vacuum state, they have the form of an electromagnetic field. In a sense, the electromagnetic field appears because now you have decided in the vacuum, you decided that the angular momentum are pointing in one particular direction, in an axis. This is what happened when you condense the system. But then this axis can oscillate. If you perturb the system beyond the real vacuum, then not only you introduce spin waves on the system, but you also make the spins, the angular momentum to oscillate, or to be able to oscillate. And these oscillations, they they have the form of an electromagnetic field, meaning that if you have a deformation of the vacuum and you want to see how the deformation of the vacuum affects the behavior of the Dirac field of one of these spin waves, then you realize that the way in which any changes on this angular momentum affect the Dirac field is precisely the same thing that when you have a coupling of the Dirac field with an electromagnetic field, meaning that these terms appear just as a substitution of the partial mu by partial mu plus a mu. You have an object there which plays the role of a mu in a particular gauge. So the only remaining thing is then to see whether the a mu's that appear in the system, which is the dynamical equations that they themselves follow. And then we have also been able to show that if you go into a very low energy regime in which this system again follow the causality, in a sense they inherit the causality of the Dirac fermions, so that the Cooper pairs themselves, they have the same causality that the Dirac fermions. Is that the Dirac fermion is the Dirac fermion is a specific combination, is a quasi-particle, but it's a specific spin wave which is traveling there, and it has this sound speed. So the electromagnetic field, this effective electromagnetic field, is sort of instead of having spin waves, you have coherent combinations or Cooper pair combinations of these very spin fields, so that they have the form of a electromagnetic field. And they can be, and because they are because the Cooper pairs they have a spin one, well, a spin they are bosons. That's why they condense. They can have coherent configurations. So you can have many different values of the amplitudes. You can have many different Cooper pairs working coherently, traveling coherently on the system, and these are what they will become photons on the system. Summarizing everything is that we have found for specific interactions between specific, but just in families. I mean, if you have some generic but some precise, as I was describing before, you have these repulsive cores, you need some characteristics, but you don't need to worry about the specific details, because the details will be the ones that are controlling the precise numbers that appear in your effective theory. But at the end of the day, you have an effective theory. In order to analyze what happened at these very low temperatures, you have something which is undistinguishable from electrodynamics. Sorry? So you have something which is undistinguishable from electrodynamics. You have Dirac fermions plus electromagnetic fields interacting with each other in exactly the same way that they are doing in the electrodynamic Lagrangian. Is there any question?
No, I think that somebody has their microphones unmuted.
Okay. So that is what happened with this emergent electromagnetism.
I do have a question, another one. So I guess you have fixed the reference frame to one of the drop somehow at some point in the beginning, and now you have these sound cones and so on, but you probably do not have something like Lorentz transformations that you can go to moving frame, and you get the same light cones in that frame. Is there any hope to get anything like this? Think about this.
The thing is that there are two different visions on the system, two different views on the system. Is that for observers that are living in the lab and they have access to the high energy theory, they perceive that that this is a Galilean world and that they have whatever velocity they like. They can analyze whether they are moving or not with respect to the drop of helium that they have there. They have access to that. But the thing is that internal observers, people that hypothetical observers that are built up by the same low energy excitations, you are building a low energy world in which you have electrons, effective electrons. This is a very simple theory. You have electron, positrons plus photons. But the thing is that all of the if you, with this physics, you can build up an observer, this observer will not be able to realize that this is embedded in a Galilean world. They will just describe their world internally as a Lorentzian world, because they will do the same things that we used to do in relativity. The clocks will change when you move with respect to another. All the effects of special relativity will be there, because you just have access to these low energy excitations. In fact, the observers themselves would be built by combinations of these low energy excitations. I mean, you have these effective electrons. In a more complicated setup, the idea is that you will have also effective positrons, effective neutrons, effective whatever. And then with this, you build up your entire theory. And then, because you are an internal observer, for you, the physics is undistinguishable from what we, in this low energy regime, is undistinguishable from the physics that we know, the physics of the standard model, if you want. But then, if you are able to probe the system at much higher energies, then you will start realizing that things are starting to break up. You will find, for example, some deviation from the dispersion relations, and at very high energies, you will find that the causality, the Lorentzian causality that is working properly in the low energy regime, start to dissolve. But this will happen at very, very high energies with respect to the energies that you are proving right now. So the same ideas. So what we want to, now we are working on the gravitational problem and trying to see whether the same line of thought can be applied to the gravitational fields. And what we are doing is to analyze different steps. Instead of doing the entire path from helium-like atoms till the emergence of a gravitational theory, what we have been analyzing is within all the steps, which are the steps that should be similar and which are the steps in which gravity has different characteristics. So that trying to first solve the problematic steps. And I can tell you that there are many of the mechanisms that are at work in the electromagnetic case. They have nice generalizations to first of all, to the linear graviton regime, and then to the nonlinear gravity regime. And in the way, there are, again, many wonderful things that appear, because some problems, some obstacles that people has been adducing, they have been saying that this is not possible to get gravitons, effective gravitons from a condensed matter-like system. When you analyze things in detail, I think that these problems start to dissolve, because there is a mechanism which is the mechanism responsible for the emergence of the gauge symmetry, which is able to bypass the problems that these people, that typically are on the literature, like I don't know, you have heard about the Weinberg-Witten theorem, for example. So what we see is that once you have a regime in which Lorentz invariance is imposed by closeness to these Fermi points, then what happens is that even though your theory can have gauge breaking terms, there is a mechanism making these gauge breaking terms to decouple from the standard degrees of freedom of GR, the two propagating degrees of freedom of GR. And we are still working on this mechanism. But for example, we have also done the same thing very recently. We have published a paper. It's already on the archive. It's in referee, but I think it will be accepted quite soon, because we are in the last stages of answering some minor referee comments. And the thing is that we have worked out the same ideas for Jan Mills theories, for example. That they have already some characteristics that are closer to gravitons, in the sense that they are naturally nonlinear. They couple the fields couple to themselves, and this adds these new characteristics that are absent in the electromagnetic case. And what we have seen there is that, again, that there is a decoupling mechanism that again, one lesson for me right now is that once you have a regime which is Lorentz invariant effectively in your dynamical equations, then it is natural that your theory produces a decoupling between some gauge invariant degrees of freedom and the other degrees of freedom that could be present in the theory, like longitudinal degrees of freedom for the electromagnetic field and all that. So again, I think the prospects, we are still working on many different details on this program, but I would stop saying that I think that this constructive way of understanding physics, I think, is a wonderful complement to other approaches more based on specific principles or assumptions, and that I think that they would have they have chances to give us new insights, very different insights from the ones that are obtained by other approaches. I mean, I don't want to extend myself, but for example, I'm working a lot on black hole physics too. Is my other research line, and the analysis on these emerging gravities theories and the way in which you construct them have already allowed us to suggest which kind of types of modifications that you should expect to see in black hole physics, for example. And this is the other main research line that I'm working on, analyzing distinct collapse process for black holes, for stars collapse into black holes, leading to a different phenomenology distinct from the standard black hole physics. But probably this is for a different talk. So I think I prefer that you ask questions if you want it.
I'm actually still confused about the previous question about Lorentz invariance at low energies. So in this helium, let's say, example or exercise that you mentioned earlier. So is it that all excitations here? So I'm not even sure if my question makes sense, because I'm not sure we have something like observers in Minkowski space that could watch, for example, photons traveling, because all your excitations are then all massless in there. So then, if that is true, then do you even have a notion of what would be an observer that is massive and not moving with sound speed, that could watch that thing and that could be transformed into, boosted into different frames and so on? Is it? Yeah.
No, go ahead. Go ahead.
Yeah, no, actually, I said everything.
Okay. The thing is that, as I said, this theory that we have worked out into the details is very simple. Of course, initially you have these massless excitations, but these massless excitations are because you don't impose any infrared cutoff to your theory. And in the moment in which you have more effects, like the system is finite, or there are many different things that, or you can have even a Higgs-like mechanism to add some masses to your excitations there, to your Dirac fields, for example. And then in this. So, as you say, this is necessary to be even closer to what we know we have in the standard model. But we know that the masses of the electrons, for example, are very, very small with respect to what we consider to be the charge of these systems. So again, for some things, electrons are very massless. So in a sense, this is approaching this idea that you have that if your system were completely ideal, you would have these massless spin waves, and you will have this direct form. But then you can build up small masses for these objects, and once you have these small masses, as you say, it's simpler to get things that could be at rest. And things that could be more similar to what we are. Of course, we are far. I mean, it is necessary to make to reproduce as much as possible all of the characteristics of the standard model, in order to be able that you have physics which is equivalent to that.
So then, if you have two different things that are closer to being at rest, and let's say moving slower than the massless excitations, but in different directions, and they would look at the same massless excitation, they would probably see it with a different speed, propagating with a different speed, or not?
Well, the thing is that in all this, in the massless case, what happened is that even though you can have you don't really measure the real momentum in the effective theory. You don't measure the momentum that is measured in the lab. Well, the velocity, if you want, the velocity of this wave, because it's living close to this Fermi point. The important point is how much it departs from the Fermi point, because this is the one that leads to the energy. If an excitation is living precisely in the Fermi point, it doesn't have energy, and is similar to not traveling or to not having momentum. So the real momentum, the one that you measure, is the deviation from the Fermi point. And then when you go to this, when you add these small masses and all that, the thing is that all of the things that you can build they cannot be pure. I mean, for example, you cannot have delta-like localized excitation, because if you have a delta-like localized excitation, then it means that it will have all the momentum, all the possible deviation from the Fermi point momentum, and then some of this momentum will be so far away from the Fermi point that they will exhibit some deviation from Lorentz invariance. But again, you have but this is in tune with the idea that quantum mechanics, well, I mean, quantum mechanics, the formalism allows to have particles with an initial distribution, which is sort of a delta function. But for example, the standard mechanism, the standard formalism, makes this delta function to immediately spread out. So here is something similar, is that the real particles are things that have some width. I mean, they cannot, because being collective excitations, they have to have a size which is at least bigger than the standard distances between the proper atoms that are the building blocks in your system. So but again, there are many things. I'm not saying that all the details have been worked out, but everything points in the direction that you will have specific regimes in which your low energy physics could be indistinguishable from at least these Minkowski, standard particle system models. Gravity is more complicated. It has additional issues.
Thank you.
If I may, this is very interesting indeed, that one can have generate from all these more complex theories from very simpler one. But am I mistaken to understand that this would imply that all the particles and fields that we understand now, so if this mechanism were in true generating our more complex interactions, and then that would mean that we have a very simple set of, let's say, real particles, like the hydrogen atoms, that are generating the world where we live, where we have more complex interactions. Would that be the implication?
Yes, the implication is that one of the implications would be that everything that we see in our world is an epiphenomena of a different layer of reality. Meaning that the electrons, that what we see as electrons, as fundamental particles, will be quasi-particles. All of quarks will be quasi-particles. So there will be an additional layer of reality. So that the interesting thing is that whether this can lead to new predictions, of course, in the sense that for me there are already some. It is funny that these prescriptions of quantum field theory works so well in many situations. Sometimes you think that many of the things that are many of the ingredients that are there would be very natural if they were coming from an effective prescription. For example, the indistinguishability of particles. I mean, this is something that, of course, you can have this abstract idea that all the electrons are equal because it's the way it is, because we have already found the last ingredients in nature, and as elementary particles, all of these ingredients are equal. But this is very, I mean, for that you have to really believe that that we are already at this stage, that there is nothing more. But instead, if you think that there is something else, then the indistinguishability of two quasi-particles is very easy to understand. because then in a quasi-particle you don't look to the details of the. You have two waves, and two waves are equal, no matter whether the precise locations of the atoms that are building up these waves, they don't matter to analyze the behavior of the wave. And so it's very simple to assert that even if there was some additional layer of in which things, I mean, you can have this, all the particles in your initial system, you can put them equal or you can put them all distinct, and it doesn't matter in order to get the effective physics, because at the end, the thing is that whether these interactions between these particles that could be different from each other, whether they can build a spin wave. And the spin wave would not worry whether this is built up of this or that. And two spin waves from the same wavelength, they will have the same appearance from the low energy perspective. So this is one example. I think there are many things on the way in which we see nature right now that would accommodate quite easily in these perspectives.
Indeed. To me, it's very exciting, the idea that we might not have to rely in quarks, or being that the most fundamental particles are particles that are by definition hidden from or are unobservable directly, which is something that just troubles me, I think. But do you think, assuming that this is the case, have you an idea of proposing a way that we could investigate what are the underlying particles? So in this case, what would be the helium atoms in our case? Is there a way that we can detect that we always, as being made by these things, will only have access to the quasi-particles?
My perspective in this program is rather different, because my interest is not so much in really know which is the next stage, this reductionist approach in which there is a next stage and there is a real thing, which is, so it's more, I don't trust very much these things unless you really have and mostly when you go to very fundamental things, because it is not the same to prove the nature of a fluid in your lab that to prove the very essence of a space-time. And I have always this worry that that we don't really know how to, if we don't have even notions of space and time, how do we make even an experiment to prove which are the building blocks of this space and time? So my perspective on that is more into the idea of this universality classes of condensed matter systems. The thing is that my interest is that if you are able to build up an effective theory which is similar to the standard model of particles, and also with gravity, by working with these things, it's just a proof of principle that many different microscopic ways of putting the information can lead to the same thing. So it's more a humble perspective, saying that maybe from the low energy perspective that we are as observers, maybe we are not going to really prove something which is at a more fundamental level, but instead what we do is to adopt a metaphysical hypothesis, which is something more coming from us, is the way in which we like to put the information. And then with this hypothesis, we work out some physics, and we see whether this works or not. And in fact, from these theories, I don't want to analyze the specific details of the microscopic of the system. What I'm just trying to get is which are the first deviation, which are still universal, which do not depend on the details of the microscopic system. So that's the thing that I trust the most, is if I get an effect that I see that is not depending, it's not specifically dependent on the specific nature of the interactions that I have put on the construction, then it's something that is worth to see whether this is in nature or not, because this would be something which, again, does not depend on the specific characteristics of this underlying thing, which for me doesn't have a complete reality, in the sense that it's just a structural language to start working on the nature of things. Is there some other question?
So, people, do you have any more questions for Carlos? We have had already quite a few of them, but I don't want to, refrain you from asking if you are interested. This is your last chance. Speak now or be silent forever. I'm joking. But in any case, as I always say, I'm guessing that Carlos will be more than fine if you contact him per email if you have any question. And I am actually curious about the paper you were referring to. If you can send me the link to it, I can circulate it.
Okay.
To have a look at it. In case, well, thanks a lot, Carlos.
Thank you for the attention.
Thank you very much.